Hi all, so our next lesson here with differential equations is something called sketching slope fields. So as we talked about last time, our goal is to be able to solve these differential equations, but sometimes we can't. Like, I have no idea what function gives me a derivative of x e to the y over y ln of x. So our next best thing, you may think it sounds silly, but it's to do something called a slope field. And maybe you've covered this in physics class with electric fields or things of that nature. They're very similar. But basically a slope field just draws your slope at a whole bunch of different points. And thankfully a differential equation, literally by definition, is giving us our slopes. So, and then the point of that is based on the slopes, you can kind of like draw out the trajectory of the graph. So even if I can't solve for it algebraically, I can still look at it and visually see what the curve is doing. So like on the left, dy dx equals 2x. And you can see if you like follow the curves here. It's looking something like this. And we kind of know, again, the solution here, the antiderivative, is y equals x squared plus some constant c. So you can see that here. We have a sea of solutions. We have y equals x squared, x squared plus 1, x squared plus 2, x squared plus 10, x squared minus 1, x squared minus 2, x squared minus whatever. You see all these solutions here. So this visually gave me the solution of what the y equals will look like, even though I knew it, I could solve it analytically. And on the right, dy dx equals y. This one's a bit harder to see, but it's something like this. And this is actually y equals ce to the x. So what function is its own derivative? It's saying derivative of y is equal to y. And we know that's e to the x. So you got e to the x, maybe 2e to the x, 3e to the x, negative e to the x, negative 2e to the x, all the way through. But slope fields are generally used with differential equations that we can't solve, and it gives us a visual of that. And I did a quick computer program here, but real programs would have many more points, and then you'd be able to cleanly see what's going on here. Here we kind of had to take some guesses because there's a lot of gaps between the points there. So how do you create a slope field? So nowadays, obviously, most things are programmed, but you'd still have to know how to program the computer to create it. And basically, you have to teach it to find a slope at every point. So we're going to do these by hand to train us in that skill. And thankfully, when you do it by hand, you're obviously not going to draw 100 slopes. You're just going to draw like a small manageable amount. So we'll go through an example. And I think you'll be good to go. So we're going to look at dy dx equals x squared minus y. Basically, at any point on the slope field that I want, I'm going to be asked to find the slope. So for example, at the point 1, 1, x is 1, y is 1. You plug that in there. You get 1 squared minus 1. You get a slope of 0. I'm just going to draw a small little line with a slope of 0. If I go to 1, 2, x is 1, y is 2. I got 1 squared minus 2. I get a slope of negative 1. And so yeah, you're just going to draw a little line there. It's negative. And the slope is negative 1, so it's kind of like a 45-degree angle. So if I go to 1, negative 1, x squared is 1, minus negative 1 is plus 1. So you get a slope of 2. So if a slope of 1 looks like this, then 2 should be steeper. And you don't need to pull out a protractor or anything. You're just going to draw something that's steeper than 1. And if I go to x equals 2, so 2 comma 1 is 4 squared minus 1 is 3. So 3 should just, again, look steeper than 2. I'm going to draw steeper. And if x is 2 and y is 2, you get 2 squared minus 2, which is a slope of 2. So then that should look like what we did here, but it'd be a bit flatter than 3. And then 2, negative 1, you get 4 minus negative 1, you get a steep slope of 5. So that's going to look very steep. And then we'll do the same thing with the last set of points. So negative 1, 1. So negative 1 squared is 1. Minus 1 is 0. If I go to negative 1, 2, negative 1 squared is 1. Minus 2 is negative 1. And negative 1, you get a slope of 2. And you're not going to be able to see much as to what the trajectory of this curve is doing, just because we have so few points. But therein is a slope field. You could see, so in the example, I found the slope at all the points. You don't need to create a table. This is just for y'all to see, and then we drew in the slope. One clarifying thing, so a slope of 0 we know is obviously a horizontal line. If you had a slope of undefined, let's say at the point 1, 0, the slope was undefined, you may be tempted to draw a vertical line, which isn't technically wrong, but out of notation, any undefined slopes, you just leave blank. So if my slope is undefined at a point, don't draw a vertical line, you just literally leave it blank. So if you see a slope field with missing points, that just means that the slope is undefined there. Right? Now is going to be your chance to shine. There's going to be a few of these. And as usual, I recommend that you hit pause, try it out, and then hit play when you're ready. So I'm just going to quickly go through this first one. So x minus y is 0. I'm just going to do these a bit in my head, and yours should look roughly like mine. So 1, 1, x 1 minus 1 is 0. In fact, let me do it a different color. 1 minus 2 is negative 1. 1 minus negative 1 is 2. So if I go to 2, so 2 comma 1, the slope there should be 1. 2 comma 2, the slope is 0. And 2 comma negative 1, the slope is getting pretty steep in 3. And if I go to negative 1, 1, so negative 1 minus 1 is negative 2. Negative 1, 2, negative 1 minus 2 is negative 3, getting quite steep. And negative 1, negative 1, negative 1 minus negative 1, the slope is 0. All right, so I'm going to hop to C, 2 to the x minus y. So if I go to 1, 1, I get 2 to the 0, which is 1. So if you go to 1, 2, you get 2 to the negative 1, which is 1/2. So that's going to be flatter than 1, something like that. If you go to 1, negative 1, you get 2 squared, which is 4, so quite steep. If you go to 2, 1, then you get 2 to the 1, which is 2. If you go to 2, 2, you get 2 to the 0, which is 1. And 1's pretty easy, it's just a 45-degree slope of 1. 2, negative 1, you get 2 to the 8th, which is very hard to show, but something like that. Very steep, 8. So if you go to negative 1, 1, you get 2 to the negative 2, which is 1/4. And that's quite flat. Negative 1, 2, it's going to be 2 to the negative 3, which is 1/8. And that's incredibly flat. So basically getting 0. And negative 1, negative 1, you get 2 to the 0, which once again is 1. X squared over y. So if I go to 1, again, you can plug in any points in any order. You don't necessarily have to start at 1, 1. So if I do anyway, so 1, 1, you get 1 squared over 1, which is 1. 1, 2, you get 1 squared over 2, which is 1/2. 1, negative 1, so you get 1 squared over negative 1, which is negative 1. So we got 2, so 2 squared is 4 over 1 is the slope of 4, quite steep. 2 squared 4 over 2 is 2, so it's still steep, but not quite as steep. And if you go to 2, negative 1, you get the slope of 4 over negative 1 or negative 4. So quite steep in the negative direction. Go negative 1, 1, so negative 1 squared is 1 over negative 1 is negative 1. And if we continue on here, so at negative 1, 1, negative 1 squared is 1 over 1 is 1. And negative 1 squared is 1 over 2 is 1/2. You notice actually my x and negative 1s and x of 1s, they're the same slopes because 1 squared and negative 1 squared is the same. And again, so if I was asked to find this point, I would have got 1 squared over 0 is undefined. I would have left it blank. So a slope field of a vertical line, you're just going to leave blank. And then lastly here, I have some good old tricks. So sine of pi over 2x plus cosine of pi over 2x. So if we go to 1, 1, sine of pi over 2 is 1, cosine of pi over 2 is 0, so I get a slope of 1. If you go to 1, 2, sine of pi over 2 is 1, cosine of pi is negative 1. So 1 plus negative 1 is 0. So you get a 1, negative 1. Sine of pi over 2 is 1. Cosine of negative pi over 2 is 0. So I get a slope of 1. Now we're going to go to x equals 2. And I'm going to just plug in a bit more efficiently here. All of these are x equals 2. If you plug in sine of pi over 2 times pi, you get sine of pi, which is 0. So I know the sine of pi term is going to give me 0. I'm just going to plug in the cosine terms. So when y is 1, cosine of pi over 2 is 0. So 0 plus 0 is 0. When y is 2, cosine of pi is negative 1. So negative 1 plus 0 is negative 1. And when y is negative 1, I get cosine of negative pi over 2, which is also 0. And then now all of these are x equals negative 1. If you plug in x equals negative 1, you get sine of negative pi over 2, which is negative 1. So the first term will be negative 1, and then I have to add it to the cosine. So when y is 1, cosine of pi over 2 is 0, so I get negative 1 plus 0, or negative 1. When y is 2, you get cosine of pi, which is negative 1. Negative 1 plus negative 1 is negative 2. And when y is negative 1, you get cosine of negative pi over 2, which is 0. So negative 1 plus 0 gives me a slope there of negative 1. Right. And now we're just going to do some matching of differential equations. And basically, you just got to figure out which of these graphs matches the differential equation. So I like to look for when the slopes are 0, what happens as x gets bigger, as y gets bigger, does it depend on x and y? And we'll look at all that. So I see number 3. Actually, we'll start with number 1. I guess we'll be consistent. And when is this 0? So it's 0 when y is 0, and when ln of x is 0, which means that x is 1. So I'm going to look at these. I'm going to try and find one of these that has a whole bunch of zeros. I guess ln negative 1 too, if we're taking the absolute value. I'm going to try and find a whole bunch of zeros when x is 1 and negative 1, and when y is 0. And, oh, I see that in C. Here x is 1, I see the zeros. Here x is negative 1, I see zeros. And the y is harder to see, but if you zoom in enough, you can see that when y is 0. Yeah, those zeros as well. So 1 matches with C. Next, I'm going to look at 2. I see dy dx is e to the 0.3x. So I see an exponential, and I kind of see an exponential just looking at it in A. But more than that, I'll notice this does not depend on y. My differential equation has nothing to do with y. See that there. So what that means is if I take an x value, and I just go up and down and change my y, my slopes shouldn't change, because my slope is not changing with y. It only depends on x. I just pick a random point, and if I go up, I see my slopes aren't changing. If I go down, I see my slopes aren't changing. Pick a random point. I go up, my slopes aren't changing. I go down, my slopes aren't changing. This only changes with x. So if you pick a point and you go left and right, you can obviously see that your slopes are changing. So 2 is going to go with A. 3, x squared minus y squared is 0. So I'm going to see when it's 0. So basically it's 0 when y is plus or minus x. I see that in B. It's like here's y equals x. So it's easy to look for the zeros. That's usually what I do first. So this goes with B. And then you can see here, again, there's other things you can do. You could like plug in a point. So if you plug in like 0, 1, you're going to have a slope of negative 1. And maybe you see that here. This is slope of negative 1. But if you plug in like 0, 2, you get a slope of negative 4. You can see here, it's getting steeper and steeper. And then I guess just out of process of elimination, this leaves D. But you can see this does not depend on x. So if I pick a random point and I change x, my slopes aren't changing. I take a random point and I change the x. If I go left and right, my slopes aren't changing. But you can see that if you change the y, it's like as you go up, the slopes are changing. And you could also see when y is 0, my slopes are undefined. And you see there's nothing here at y equals 0. To a bunch of emptiness. And the other analysis you can do, you can see as y is getting bigger, 4 over y gets smaller. So as y gets bigger, my slopes get flatter. And you can see that here. You pick a value. As y is getting bigger, the slopes are getting flatter and flatter. That's it on slope fields. By now you should be able to sketch them and then be able to use logic to figure out which differential equation matches which slope field. Again, you can do that by finding the zeros, seeing when they're undefined, looking, does it depend on x and y? As x gets bigger, what happens to my slopes? As y gets bigger, what happens to my slopes? Then, if needed, some more obscure things you can do. You could see, hey, in quadrant 1, what should my slopes be? Positive, negative, mixed. In quadrant 2, what should my slopes be? You can plug in points, get slopes, and then check it. There's many options here on working with slope fields. Alrighty, y'all.